Alright, so what we're looking at now is what we call a chi-square test. And when we do chi-square tests, we're still dealing with categorical data, but now we're not just testing a proportion, or we're not just comparing two proportions, but we're looking at the distribution of categorical data across probably several groups. So for instance, let's say that we're in a very diverse community like New York City, and we want to see that the fire department, that the demographics of the fire department match the demographics of the people in the city that it's serving. So if you think about the demographics, you'd have white, you'd have black, you'd have Asian, you'd have Hispanic, you'd have other. So what we would be doing is we'd be testing that distribution of firefighters across the department, across the compared to the distribution of people in the city. So we're not just testing one proportion, we're testing the distribution of all of those categories versus the distribution of all of those categories that are in the city. So we no longer use a z distribution, so we use this thing called a chi-square distribution, which is in front of you. And this chi-square distribution is a dynamic distribution, and that is it changes shape depending on this measure here. This df here is called degrees of freedom, and degrees of freedom is a measure of how many different categories you're comparing. And I'll go into that calculation. It's fairly easy to do, but what you're going to see is as degrees of freedom starts to increase, I have it set at 2 right now, what you're going to see is the shape changes. And what you're going to notice is it's not a symmetric distribution, it's a skew distribution. So that's going to be a little bit different than dealing with a z distribution. However, your p-value is always going to be, if you were to find whatever your p-value is, it's always going to be the area to the right of whatever that chi-squared statistic is. So we would never have a two-tailed chi-squared test. We'd only have a one-tailed test, and it's always to the right. So that's basically how we're going to use this here. Now, even if we increase this, you'll see as our degrees of freedom increases, and again, if we were testing like 10 different categories, that would be a lot of categories. So very rarely would we do a test where we'd have 10 degrees of freedom. But you see it becomes more symmetric, but it'll never become completely symmetric. So you're always going to be dealing with a distribution that's slightly skewed right, and you're always going to be dealing with the area. The chi-squared statistic is whatever you calculate it out to be, and you're always going to be looking at the area to the right of that statistic on the distribution. Alright, so let's talk about chi-square. Chi-square is a test, again, we're dealing with for 1 and 2 categorical variables. Okay, so we're still dealing with categorical data. Okay, data is usually presented in some form of a table divided into categories. Okay, so usually that's the giveaway. I mean, usually when you'll see when you have data that's in tabular form, then they ask you to prove something using inference, then you know it's a chi-square test. And it's categorical data. I mean, you can get data in a table form that's not categorical data, and then you're not dealing with chi-squared. But and then data must be in the form of counts for each category. Okay. Now, as I pointed out, the chi-square distribution is skewed right, or something like that, depending on the degrees of freedom. Okay. And it looks like that. And when we're talking about it, we know it's skewed right, it's not symmetric. The degrees of freedom, are not determined by sample size but by number of categories. Okay, and the reason I write that is when we do t-tests, the degrees of freedom are determined by the sample size. But in the chi-squared test, they're not. Chi-squared doesn't care what the sample size is, it just cares about how many categories you're testing. It's only one-tailed in nature, and again, you're going to calculate like you did with a proportions test. You calculated a z-value, and you tested the area of that z-value that was either above or below. But here you're going to test a chi-squared value, and whatever that chi-squared calculates out to be, you're only going to test that area to the right, and that area to the right is going to be your p-value. Now, you're going to reject or fail to reject the exact same way. It's not going to change. I mean, if your alpha level is at 0.05, let's say, then you would reject anything that's below 0.05. If it's 0.10, then you reject anything that's below 0.10. Okay, but your p-value is still going to be the same type of valuation you did with a z-distribution. The only difference is you're using a different calculation to get it. The distribution here is dynamic, not static like a z-distribution. It changes as degrees of freedom changes, and I showed you that on the applet. If your degrees of freedom get larger, then it tends to get more symmetric. If your degrees of freedom are smaller, then it's very skewed right. And the p-value is the area to the right of the chi-squared statistic. Okay, so that's an overview of the chi-squared. Alright, so our chi-squared tests are a goodness of fit test, and that's a test that the fit of a sample to an expected distribution. Okay. So for instance, let's say that this right here is a distribution of all cars in the United States. So if we were to go down and do a cluster sample of cars in a parking lot, and we were to compare it to this distribution, that might tell us some things. Okay. Let's say that we go down and let's say 50% of the cars in the parking lot are of European origin. Well, what that might tell you is that you're dealing with a fairly affluent community. So if that's true, then we may choose to market things a little bit differently than if we were to go down into, let's say, a community in, let's say, rural Pennsylvania. Let's say that 67% of the cars were American. Maybe they're Fords or Chevys or Chryslers. We might do things a little bit differently down there than we would in a community where most of the cars are of a European type. And then you might get a distribution that fits this pretty closely. Now this, what I've shown you, is the expected distribution of cars. That's the distribution of cars in the entire United States. So when we go down and get our observed distribution, how well does it fit this? And that's basically how we would do a chi-squared test. Okay. But the second kind of test is a homogeneity test. We test category percentages across homogeneous group. Homogeneous means we're looking at one group of people divided into separate categories. So for instance, let's say we were to look in Norwalk, and we were to look at Democrats, Republicans, and Independents. Well, if we're looking at people in Norwalk, we might divide them into males and females. However, they are a homogeneous group of people. They are all Norwalk residents. So all we've done is we've taken a homogeneous group of people and divided them into separate categories. Hence, we were looking to see if the distribution of male political affiliation in Norwalk is the same as the political affiliation of females in Norwalk. So that is that's a homogeneity test. Okay? And then the last test is an independence test. Now, an independence test is when we test different groups or heterogeneous groups and see if those categories are the same. So, down here, we do a test now. We're testing to look at political affiliation, but now we're looking at Norwalk residents versus Stamford residents. Okay, and again, these are not homogeneous groups. These are heterogeneous groups. Okay, these are people that live in different communities. So now we're looking to see is there an association? So, for instance, the people in Norwalk tend to be more Democrat and people in Stamford tend to be more Republican? Or is there no evidence of an association, of which we would say that they're independent? So we would say whether you're dealing with people in Norwalk or Stamford, political affiliation is independent of which town you're looking at. So they have approximately the same distribution of Democrats, Republicans, and independents in that town. And those are basically your three chi-square tests that you'll be using in this chapter. Alright, so the next thing you got to do are the conditions. So there are only three conditions in a chi-square test. Because again, we're not testing necessarily just one sample, we're testing a distribution. So the first thing is your sample or your observed values that you're getting these from must be random or representative of the population. So that is what this is. This sample must be random or representative. Okay. Obviously, if it's not, then it's useless. Counts. Data are in counts. Percentages must be changed to counts. Okay, so for instance, in this, if we were given this distribution, and let's say that we looked at 1,000 cars, okay, this distribution right here, then we would simply change this to, we would have 400 expected American cars, 350 expected Japanese Korean cars, and 250 expected European cars. Okay, so sometimes these things will be given you in percentages, but you have to change them to counts. Okay, and the last thing is this ECF, expected cell frequency. Those must be greater than 5, and basically I'll show you how to get the expected cell frequencies when we're going through the problems. So that's just a condition we're going to keep in the back of our minds right now, and as we go through the problems, I'll show you how to calculate those. Alright, so let's look at the chi-squared calculation, and this is on your AP formula sheet. And basically chi-squared is going to equal the sum of each observed value minus the expected quantity squared over the expected value. Okay, so that's basically going to be the calculation that you'll use for every chi-squared test that you're going to do. Alright, so we're going to look at our first type of chi-squared test, and this is a college students problem, and we got a Philadelphia newspaper report claims the distribution of students who attend a local college are as follows, and we have 4 different percentages that are supposed to fit into different states that students come from, and then down below we have the actual observed values, which are down here. This is where the students come from, so these are where we expect them to come from historically, I guess, based on historical data, and this is where our students are actually coming from. So what we're dealing with here is we're dealing with categorical data. Okay, we're not dealing with quantitative data because we're dealing with where students come from, so they fit into a category. Okay, and we're not just dealing with one proportion. Notice we're dealing with 4 different proportions. So we're not just testing one proportion, we're testing that all of the proportions are approximately what we think they are. So in this case, we're not going to just test a p, we're going to be testing several p's. Okay, and hence we're testing a distribution. So here's how I'm going to teach you to do it. There are a couple of ways to do it, and I'll talk you through those. If you want to do it an alternative way, that's fine. Now our parameter could be what all those p's are, and we could list it as p sub d is proportion of students from Delaware, p sub n is the proportion of students from New Jersey, so forth and so on. However, that's not the way I do it, because when I'm dealing with a chi-squared, I'm dealing with a distribution. So my parameter here is simply going to be the distribution of home states of students at a local college. Hence, I'm testing the distribution. That's the parameter. Okay, I'm seeing if the observed distribution matches what the expected distribution is. Not that any one proportion matches what I think that proportion should be. So I'm testing all of these different proportions. Okay, so my null hypothesis is the distribution is as expected, and the alternative hypothesis is the distribution is not as expected. Now you might be saying, well, hold on, every time we do a hypothesis or a parameter, we always have a symbol. You know, we have a p, we have a mu, okay, we'll have a beta. So, you know, why don't we have a symbol here? Because we're testing several p's. So your null hypothesis, this here could really read, for instance, that p sub d equals 0.241, and p sub n equals 0.154, and p sub p would be 0.507, and p sub o would be 0.098. And you would define all of those p's up here in your parameters. You would have 4 different, in essence, you're testing 4 different parameters to see if that entire distribution matches. And then the alternative hypothesis would be that each of those parameters does not equal what you think it should. So if you're comfortable using symbols, then you would just list all of the different proportions here, and you would just have the right, you know, for your parameter, you would have the right, you know, what each of these means. And then for the null hypothesis, you would have to list, you know, 4 different p-values. And then the alternative, you would have to list 4 different p-values. In the null hypothesis, you would have p equals, and in the alternative, you would have p does not equal, and you would have that for all 4 proportions. I just find it easier to just test the distribution. Okay, I'm not really testing one p, so that's how I go about it, and this is perfectly acceptable. Okay, so our assumptions and conditions. If you remember from the first page, is the data random or representative? It says that these students were randomly chosen, so data was randomly chosen. And then we needed that the data is in counts. Now, our observed value, I'm just going to put an O here because this is our observed value is in counts. Okay. Now, our expected values are not. Our expected values are in percentages. So those are all right here. So we got to change those all to counts. Now there's 150 students, so we have to do each of these percentages, and I've kind of already done those. I'm going to put those right here. Okay. and those come out to 36.15, and for Delaware and 23.1 for New Jersey, and 76.05 for Pennsylvania, and 14.7 for other. Now, when you're looking at your data, your expected values can be decimals because they're what you expect them to be. So hypothetically, you might be saying, well, how can I expect to have 36.15 students? You can't have 0.15 students, and you're right. But when we're dealing with expected values, we're dealing with kind of a hypothetical, not the actual. Okay? So the expected values are allowed to be decimals. The observed values are not allowed to be decimals. Those are the actual people that you would be counting. And if data is in counts, you cannot have a decimal. Okay, so observed values can never be decimals. If you put a decimal in, your calculator is going to get really upset at you, and you're going to wind up getting errors, and you're going to be like, I don't understand what's going on. Okay. We do leave the expected values as decimals for accuracy's sake. Okay. So just keep that in mind. And then the last thing is that all of our expected values, our ECFs, are at least 5. So here are all of our expected values. So we're going to put all of ECFs, or expected values, are at least 5. Or you could just put all ECFs are greater than or equal to 5. Either one is fine. You can put that either way. Okay. Name the test. This is a chi-squared goodness of fit test. Goodness of fit tests are when you're just giving one distribution without a contingency table. And right now we haven't gone into contingency tables, but after we do, you'll know the difference. Okay, so basically here's the expected distribution. Here's the actual distribution. How well does this fit what we expect it to be? That's a goodness of fit test. Very simple. Okay. Okay, so now we need test parameters and statistics. Well, we need the expected values on our paper. Those are done. Okay, that's really the only calculation we had to do. And then we have to do this thing called degrees of freedom. And the degrees of freedom is simply the number of categories minus 1. So in this case, we have 1, 2, 3, 4 categories. So our degrees of freedom is simply 4 minus 1, and that's 3. So in this case, we're dealing with 3 degrees of freedom. Now we got to obtain the p-value. Okay, so we go back to this whole calculation up here, right? This chi-squared is the sum of observed minus expected squared over expected. So let me show you what this would look like. We would take each of our here's our observed values, and here's our expected values. So we take each of those. So for New Jersey, Delaware, it's 30 observed minus an expected of 36.15, and we square it. We square those differences, and why do we square those? Well, to make them positive, and then we divide by the expected. Okay, and then we do it for the next one. We add that, and now New Jersey is 39 minus 23.1 quantity squared over 23.1. And then we do it for Penn, and you do that. Okay. And then you would do it for other, and other is the plus signs, 10 minus 14.7 quantity squared over 14.7. Okay. And if you were to do this math, you would get a sum of 13.83. Not going to sit there and do it on a calculator, and you're not either. I'm just showing you what that calculation is. Okay. Now, Once you get that sum, um, you could go into the calculator and just go to distribution and then find your second distribution, and then there's chi-squared CDF, just like you would do norm CDF. And our lower bound would be 13.83, and make the upper bound like 100, and then degrees of freedom is 3, and our p-value is like 0.003. So that's the mathematics behind it. Okay. However, your calculator does do it for you, and I'll show you how to do that. In a goodness of fit test, you're going to go into list, and you're going to put in your observed values in list 1 and your expected values in list 2, keeping in mind your observed values can never be a decimal. If you put a decimal in your observed value, your calculator is going to give you an error. And do not round your expected values. Again, they're hypothetical, so just round them to 2 decimal places. Do not round them to a whole number, and leave them alone. Okay. From there, you're going to go to stat tests, and you need a TI-84 for this. If you have a TI-83, you're not going to have this. You're going to go to chi-squared goodness of fit test, and goodness of fit test is the one that uses the lists. So my observed values are in list 1, my expected are in list 2, and my degrees of freedom is 3. And then I say, okay, calculator, draw that out for me. Okay? And look what happens. You get your chi-squared value, it calculates that for you, and it gives you the p-value. So if I was doing this on a test, given this data, I would show the calculation like this. I would put the first one plus dot 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 all the way to the last one. Okay. And then I would say, okay, well that equals 13.8285. And then I would calculate, I would copy this down. Now you notice it's not showing a shaded region because it's way over here. So our chi-squared test looks like this, and it has a p-value of 0.0031. So assuming that we're testing this at the, yep, it says we're testing this at the alpha is 0.05 level. So we reject H of O at the 0.05 level. Okay. Since our p-value is less than 1%. And then what we would do is we got to state the conclusion. So in this case, there is strong evidence that the distribution of home states of students is not as expected. Now, that's not enough of a response yet. We need, when we reject a null, we need to kind of go into it a little bit. So we go and we start looking. And I want to see where there's significant differences. So when I look here, New Jersey has many more than expected right there. And Delaware has less than expected, Pennsylvania has less than expected, and New Jersey has more than expected. So I would just put Delaware, Pennsylvania, and other have less than expected, while New Jersey has significantly more, about 16, significantly more, approximately 16. More than expected. And therefore I've kind of analyzed what what's wrong with the distribution. Okay, so there it is. That's how we do a goodness of fit test. And just make sure when you come down to that conclusion, when you reject, that you don't just say, okay, yeah, we reject it. There's strong evidence that the distribution is not as expected. How is it different? Go into it a little bit with some detail and show where the differences are. All right, so here is the next kind of test. All right, now right away you see that the data is presented differently. So you're dealing with a table. Okay, you're dealing with a table of values, not a list, not a given distribution. Okay, so whenever you are given a table of values like this, the goodness of fit test is out. That's out. It's definitely not a goodness of fit test. So it's got to be a homogeneity test or an independence test. Okay. So we're going to deal with one of those two when we're given data presented like this. Now, what's the difference? Well, the difference, as I showed you before, if I can find my paper, yeah. Remember, I went into and I said, okay, we're dealing with homogeneity test, is we're dealing with one group of people across several categories. So if we're looking at the town of Norwalk and we split the town of Norwalk into males and females and we look at their political affiliation, we're looking at a homogeneous group. We're looking at people in Norwalk. However, if we look at people in Norwalk versus people in Stanford across their political affiliation, we're looking at heterogeneous groups. We're looking at two different groups of people across different categories. So in this case, we're looking at students at a local high school. So that's a homogeneous group. Okay. We're looking at students at a local high school who took the AP Calculus AB exam, and we're looking at their results. So this is going to be a homogeneity test. Okay. So we're going to go through this, and I'll show you how to knock this out. So our also, before I go on, notice the question that says, is there evidence of a change in distribution? Usually if there's a change in distribution, if it's an independence test, you'll know by the wording, and I'll show you that when we get to it. Usually a change in distribution implies you're dealing with one group across several categories. Okay. So the parameter is the distribution of AP Calculus scores. So our null hypothesis, again, has the is there evidence that there's a change? So the distribution, the null hypothesis is the distribution has not changed, and the alternative is the distribution has changed. Yeah. Now, our assumptions. Now notice, just like a goodness of fit test, we're testing a distribution. All right, and in all chi-square tests, we're always testing the distribution. Okay, we're not just testing the proportion of fives, for instance. Is there evidence that the proportion of fives is the same for each of the 3 years? Well, no, we're testing the entire distribution. So our data is in counts. It's not presented in percents. These are all the counts right there. Okay. It doesn't say that the data is drawn from a random sample, so we'll say the data is representative of all AP calculus students at this school. And the last is our ECF condition, right? Our expected cell frequency. Okay, well, we don't have the expected values, do we? They're not given. We're given the observed values. Okay. Well, if I was to look in 2008 for the number of 5s I would expect, well, how many 5s would I expect? Well, I would expect 44 out of 119. Right? So I would do the proportion of 5s, if the distribution hasn't changed, should be approximately 44 out of 119 times the number of people in 2008. So to do 2008, I would do 44 divided by 119, that's the proportion of 5s, times the number of people in 2008, which would be 43. And I would do the same thing in 2009. I would do 44 over 119 times 41 and 44 over 119 times 35. Well, if you notice, here's the shortcut to doing this. Really what you're doing is this represents, the 44 represents the row total, and this represents the column total, and this represents the total. So to get an ECF, here's the easy way to, instead of trying to remember the mathematics behind it, a nice easy way of doing it is your ECF, just do the row total times the column total divided by the total. So just do the 43 times the 44 divided by 119. And that's what we're going to wind up doing. 43 times 44 divided by 119. We're going to do 15.9. And I'm going to do 41 divided by times 44 divided by 119. That's 15.16. And then 35 times 44 divided by 119, and that's 12.94. And then we're going to do the 3s, so 43 times 36 divided by 119. 13.01, and then 41 times 36 divided by 119 is 12.4. And notice I don't round the expected values. 35 times 36 divided by 119 is 10.59. And then we'll do the 3s. So 43 times 39 divided by 119 is 14.09, and then 41 times 39 divided by 119 is 13.44. Looks like we're going to be good here. All these are above 5. 35 times 39 divided by 119, 11.47. All right, we're good. So all of our ECFs are at least 5. So we've met all of our conditions. Okay. So name test, you know what, if you're on it and you just call it, if you just put chi-squared, I mean, I think that would fly. You know, technically this is a homogeneity test. Okay. All right. So again, our test statistics. Now we got all of our expected values. They're all right there. Now we got to get degrees of freedom. Now, when we're dealing with a contingency table, remember we did, when we were doing a goodness of fit test, it was just categories -1, right? When we're dealing with a table, we're going to do rows -1 times columns -1. Okay. So in this case, we have 1, 2, 3 rows. So that would be 2. 3 minus 1 is 2. And we have 1, 2, 3 columns. Okay, 3 rows, 3 columns. So we would do 2 times 2, and that's 4 degrees of freedom. Okay? Now to obtain P, if we were to do the mathematics in this whole thing out, we would have to do 9 calculations and add them all together. We'd have to do each observed value minus expected squared, the quantity squared divided by the expected, and then add up all 9 of those different values that we got. We're not going to do that. So we're going to cheat, going to let the calculator do it, but we have to put down our work. So we're going to put down that chi-squared equals, I'm going to put down the first one, observed is 18, minus expected of 15.9, quantity squared over 15.9. Okay? And then I'm going to say, let's add that all the way to the last one, and that would be 13 minus 11.47, quantity squared over 11.47. And what does that equal? I don't know yet. We'll figure it out. Let's put an equal sign there. Okay? Now, when you're dealing with a table, very easy. Okay, you don't put it into a list. You only put it into a list when you're given one distribution. And it says, okay, this is what the distribution should look like. You're not given that here. You're given a table. So, the way we do a table is we go to a matrix. The matrix button is the second in this x minus 1 here. So second x minus 1. Okay? And we're going to go and we're going to say, okay, let's edit the first matrix. Okay? And it's going to ask you what's the size of the matrix. Now, matrices are defined on your calculator as number of rows times number of columns. So we have 3 rows and 3 columns. Okay? And then it's going to give you a blank matrix with all zeros. And what you're going to do is you're going to pop the observed values in. So you got 18, you got 13, you got 12. And we're going to go 15, 12, and 14. And then we're going to go 11, 11, 13. Okay? So that is what your observed values look like. Remember, observed values can never be decimals. Okay? Just like in a goodness of fit test. Then we're going to go to step, and we're going to go to test, and we're going to go the chi-squared. Now, goodness of fit, this isn't a goodness of fit test. Goodness of fit tests use lists. We're not using lists. We're going to go to chi-squared test. Now, the calculator doesn't differentiate between a homogeneity test and an independence test. All it knows is that you're using a table. So whenever you're using a table, go to the chi-squared test. And you're going to say, okay, the calculator is asking you, where's your observed list? It's an A. Don't worry about the expected. You don't have to do it. The calculator will do that. Okay? And I'm going to say, okay, calculator, draw that up for us, right? So, what happened is we got a fairly high p-value. Okay, so the chi-squared is 1.1378. So we're going to put that on our paper. And I'm just going to draw this thing somewhere on my paper out of the way. And we're going to shade in a good part of that like that. And I'm going to put a p-value of 0.8882. Okay, so now before I go on, I just want to show you something. If you go back into matrix, now you notice it filled out matrix B for you. You notice you didn't put down that matrix B was 3 by 3. The calculator kind of did that for you. And if you just push enter, you're going to notice that those are all your expected values. And look what happens. Those match up. That's 15.9 up here, and then 13.01, and then 14.09, and then 15.16, 12.4, and then 13.44, and then 15, ooh, that one was off, 15.16, did I do that right? 22, 35, what I did it right? Apparently ours was off. Alright, so these are off. I don't know why I did those wrong. No, did I? No, okay, no, we're not off, we're off, we're good. Alright, so all of our expected values came out to be correct. Now, you're going to ask the question, can I just run the test and not worry about calculating those on my own? And the answer is yes and no. If you're given this as a free response question, feel free to do it that way. Okay, but I'm going to warn you on a multiple choice, what they're going to do is they're going to do something like, they're not going to give you this, and they're not going to give you these cells right here. They're gonna blank out part of this thing, and they're going to say, okay, here's the row total, and here's the column total, and here's the total. What's the expected here? And you're not going to be able to pop that whole thing in your calculator and figure it out. So you do need to know how to do this, and it's pretty simple. I mean, you just take the row total, multiply times the column total, and then just divide it by the total. So you can find these expected values on a free response question however you want to. They have to go on your paper. Okay, they have to be on your paper. So however you choose to do them, I don't have a preference on a free response question, but they got to get on your paper somehow. Okay. However, you do need to know how to do this, because that is going to show up on a multiple choice question. They always do. So this one's pretty simple. Make a decision. We're going to fail to reject H of O at the 0.05 level, though they didn't tell us that. We'll just say we're done at the 0.05 level, and state our conclusion. There is no evidence that the distribution of AP Calculus scores has changed from 2008 to 2010. That was simple. Okay, so that problem is done. Alright, so the last problem we're going to do is this problem called handedness, and basically we're looking here at a random sample of students' eye color and handedness. That should be, I'll take that out, are as shown in the table above. Is there evidence of an association between eye color and dominant hand? Okay, so what we're looking at here is we're looking at two different groups of people. Okay, we're looking at left-handed people versus right-handed people. So these are not homogeneous groups, these are heterogeneous groups. Okay. Now the dead tip-off as to what kind of question you're dealing with here is this word right there. Whenever you see that red flag, you know what you're dealing with. You're dealing with an independence test. Okay. So whenever they ask if there's an association, you know that you're dealing with an independence test. Okay. So our parameter here is going to be the distribution of eye color across left and right-handed students over here. Yes, students. Okay. Okay. Now, the hypothesis. Well, we're looking for evidence of an association. So think of it this way: if we were to write our hypothesis or our parameter in terms of p's, we would have the proportion of brown eyes, so, and the proportion of blue eyes, and the proportion of what, green and other. Okay. All right. Now we would be comparing left and right-handed people, right? So if we made two segmented bar charts, one for left-handed people and one for right-handed people, and we put them into percentages, our null hypothesis would be that these proportions, so the proportion of brown eyes for left-handed people equals the proportion of brown eye for right-eyed people. That would be our null, right? Well, if that was true, then, you know, brown and brown would be equal, and blue would be about equal, and then green say most people are green, I don't know, green and green, and then some other color. Okay. And all of these proportions would be approximately the same. That would be our null hypothesis. Now, if they were approximately the same, then our segmented bar chart would look the same. If our segmented bar chart looked the same, then we would say that eye color is independent of dominant hand. Okay? So, hence what that brings us to is that the null hypothesis is, really you could say there is no association between eye color and dominant hand, but when there's no association, what does that really mean? And you wouldn't be wrong in writing it that way. If you write it that way, that's okay. But what you're really saying is eye color is independent of dominant hand. Okay. The alternative is there is an association. That's what we're trying to prove, right? There is an association between eye color and dominant hand. Okay. Now, if there was an association, then these would not be the same. Those two bars would not look the same, and then we would say, okay, well, you know, left-handed people tend to be brown-eyed while right-handed people tend to be blue-eyed or something like that. So that's basically the alternative. Okay. The assumptions, this is a random sample. Students, data is in counts. All right. Now we got to do the ECFs, right? So I'm just going to knock them out on the calculator. Remember, all it is, you know, if I wanted to know browns, I would just do 42 divided by 114 times 119. I'm sorry, times 19, because there are 19 people that are left-handed. So I just do row times row total times column total divided by the total. So I'm going to do all the left-handeds first. So 19 times 42 divided by 114, and that comes out to be 7. 19 times 33 divided by 114, that's 5.5. And then 19 times 23 divided by 114, that's 3.83. And then 19 times 16 divided by 114 is 2.67. And then I'm going to do the right-handed, so 45 times 42 divided by 114, 16.58. And then 95 times 33 divided by 114 is 27.5. And then 95 times 23 divided by 114 is 19.17. And then 95 times 16 divided by 114, that's 13.33. Okay, well, now we have a problem. Okay, and the problem is these two right here. Our expected values are not all at least 5. So what we're going to do here is we're going to combine here. So we're going to have left and right, and brown is going to stay as 6 and 7 and 36 and 16.58. Blue is okay, 7 and 5.5, and then 26 and 27.5, and I'm going to combine green and other. Okay, so we're going to make green and other, and that's going to become 2 plus 4 is 6, and then 3.83 plus 2.67 is 6.5, and then this is going to become 21 plus 12, 33, and then 19.17 plus 13.33 is going to be 32.5. Okay, so That is going to be our observed and our expected values. So now all of our ECS are at least 5. So sometimes you've got to combine some categories to make it go. Name the test. Again, chi-square test for independence. Test statistics and parameters. So we got the expected values. They're all there. Now our degrees of freedom, we're going to work off of this. Okay, so it's rows minus 1. So there's 1, 2, 3 rows. And there's 1, 2 columns. So there's 2 degrees of freedoms. Obtain P. So I'm going to do chi-squared equals 6 minus 7 quantity squared divided by 7 plus dot 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 33 minus 32.5 divided by 32.5. This should be squared on top. We don't know what that equals yet. So now we go to matrix. Okay. And how we're going to edit matrix A. And let's see, we have 3 by 2. And we're going to put in the observed values. So 6, 7, and 6, and then 36, 26, and 33. Okay. So those are what our matrix is going to look like. And then we're going to go to stat. No, we're not. We're going to go, stat test, chi-squared. Remember, we use a chi-squared test whenever we use a table. And we're going to say, okay, calc, go ahead and draw that up for us. So our chi-squared value is 0.7085. And, you know, notice with a small degrees of freedom, it just bends down, right? And it's P equals 0.7017. Okay, and again, if I wanted to go in and test, just check matrix B, I could. So if I go to matrix B, just knock it in. I get the 7 and the 5.5 and the 6.5, and then the 35. 35? Is that 35? Yeah, that is 35, isn't it? That should have been 35. Okay. 95 times 42 is 35. Yeah, I made a mistake there. That should have been 35. And that's 27.5 and 32.5. I must have punched something in wrong. 95 times 42 divided by 114. Yeah, I punched something in wrong. So that should have been 35. So that's why it's good to go back and check it. But that's what we got. And then make a decision. So this time we fail reject. H sub O at the 0.05 level. And so what do we say? Now again, be careful. Don't say that these are independent, because that's accepting the null hypothesis. Okay, so all you say is there is no evidence of an association between eye color and dominant hand. And that's it. So that's a chi-squared independence test from start to finish.